Welcome to this talk. I'm going to talk about backpropagation in three parts, which is the secret sauce of AI and the magic of the PyTorch framework. Who is this presentation for? It's anyone not in the technical weeds on a daily basis, but who would still like a technical overview and appreciation of this major underlying principle of AI, backpropagation. We will require some high school calculus, differentiation and some computation theory, but only to a appreciation level. You will have some technical background, but not necessarily hands-on. Why then yet another explanation? There are plenty of good explanations on the internet of backpropagation, but they tend to range from very simplistic overviews to mathematically cumbersome ones, and none of them appear to be able to bring together three major facets of backpropagation, namely the conceptually, why does a neural network do what it does, what's it trying to do. That will be the high level explanation, that's part one of this talk. Then the mathematical concepts, which is the kind of mid-level. How does the underlying functions work in terms of actually achieving learning? And then the computational level, or the low level, which is the part three, which is how does PyTorch actually do all of this stuff? So that's the goal, to kind of bring it all together in one holistic explanation. To ease the explanation, we don't use the classical neural network equations to begin with. Simply because there's no need to understand what a neural network does and how backpropagation works, indeed all the way down to the details of the underlying PyTorch library. We don't really need to know the details, the mathematical details of each layer of a neural network. We will show eventually how we can introduce that kind of detail, and it makes no difference to the way PyTorch really works. So to avoid cumbersome mathematics, for the sake of being true to the perceptron model, we don't need to do that, so we dispense with it here. Also, I'm going to somewhat mix and simplify the mathematical notation and stray a little bit from the formal math that we might use in a research paper. That's so it makes it a lot easier to understand again. The idea of this is to elevate your understanding. It's not to be necessarily faithful to the mathematical notation and the perceptron algorithm and all of the mathematical details that don't really aid in our understanding of the concept at the holistic level. So part one then is this high level concept, function approximation and learning. How does the neural network learn? What is it trying to do? We need to really understand that in order to sort of locate and contextualize the concept of backpropagation. So here's our assumption, or our kind of context. We're going to imagine that we have some system in the real world. In this case, it's website analytics. We're measuring the visits to a website, the number of clicks, the number of likes, the product saves, all of those kinds of things, social shares and so on and so forth. So this is a set of historical data we have about users visiting a website. And we also have some historical pattern of buying history for all of the users that visited the site, which of them bought, which of them didn't, how much did they buy, when did they buy. There's all kinds of ways we could characterize the buying. But there is an assumption here that there is a hidden pattern in this data, some underlying or latent function, which we're going to call h of x, which is our target function. However, we don't know what it is. This is the key thing. There's no mathematics. You can't open some math book and say, oh, give me the equation for the buying history of a buyer on a website. It's just too difficult. The website itself, each website is different. The way we measure them is different. There's no way we can write a mathematical closed form or analytical function that would relate the website analytics to the buying history. So we need some method to discover this hidden or latent function. And that's the concept of a neural network. It's some black box that contains a network of functions that are configurable and we're showing the configuration here nominally via some sliders, like a mixing desk or whatever. And depending on the configuration of that function, the hope is that if we give it the website analytics, it can in fact predict the buying history in a way that allows us to predict the buying propensity for a new user on the website, one that we haven't seen yet. So their data is new and hasn't been seen. And this characteristic of going from the seen data to unseen data and the function still working is called generalization. So we're hoping then that this neural network can model a function inside of itself that somewhat approximates this hidden function, which we don't know, but we're going to discover it through analyzing the data that we have available about this real world system. And in this regard, a neural network is often referred to as a universal function approximator. It can approximate any function, and in this case we're interested in hidden functions in the real world, to do with perhaps business, say. So let's look then at a trivial example. Say we had two sets of data as a sample of some process, some business process, but unlikely here, but let's just go with it. And we have a set of data X and a set of data Y, and they're related in some fashion. And here we can see clearly that the Y is just X squared, and that's the way we've set this example up. So our sample has the X data and the Y data, but this function Y equals X squared we're going to assume is unknown. So the idea then is that we show the data to our neural network. It does something, we're going to discuss what, to see if it can learn how X relates to Y, how our feature X relates to our target variable Y, but without knowing that there is indeed an underlying function. In this case we set it to be Y equals X squared, but the neural network doesn't know that, and indeed for any useful business problem it is unknowable anyway. So having then learned that relationship, the idea is that we could dispense with the target variable Y. We could just feed in then our feature X, and then we would expect, if the neural network has learned the underlying function, that for every X we put in, we get the predicted Y out is in fact something like the square of that data. So now we can say that our model function f of X is approximately X squared. A neural network will never 100% discover the underlying function, because for statistical reasons and to do with noise and how big is our data sample, and we'll get into some of those details in a minute. But the idea is the hope that we can sufficiently approximate a hidden function that we can do something useful with it. But how do we know if it's really learned the function and not just memorized the data that we've shown it? It could just memorize that 1 maps to 1, 2 maps to 4, 3 maps to 9, and it doesn't really know what the function is. It's just kind of like mimicking it. Well, we could take a new input that it hasn't seen before, so it's not in the sample, so therefore we call this out of sample data, and then we could see, okay, what happens when we feed that in. Now, if it had memorized the answers, it wouldn't know what to do with 10, and it would just produce some maybe wildly out of sync guess. But if it did indeed produce the square of 10, 100, then we might suppose that the network really has learned the underlying function. So how do we know then that it has learned something and not memorized? Well, if the learn function generalizes, we call this, to handle new, unseen, what we call out of sample data, to still give the right prediction, then we actually are reasonably confident that the neural network has indeed learned the actual underlying function as opposed to memorize the data. So we can now have some degree of belief, confidence that the model function f of X is indeed some approximation of the hidden or target function h of X. But The problem is most business real world quote unquote systems do not have mathematically tidy or knowable functions like y equals x squared. If we, for example, imagine we're trying to characterize some smart city, which is, a big use case for AI, we might have data like traffic lights, taxi speed, sensors, weather predictions, and camera data from computer vision. And these are our features that we feed into the network. And maybe what we're trying to discover is some underlying traffic prediction function that tells us a reasonably accurate forecast of traffic densities around the city. Again, we don't know what this function is. There's no mathematics book. There's no algorithm we can look up. There's nothing we can look up that would tell us how to map the input data to forecasts of traffic densities. It's some complex hidden function, latent function, and our hope is that the neural network would learn it. So the question is, how do we learn this function? Well, we're going to get to that. Another example, we may have scanned images. In this case, we're showing a scanned image of a handwritten digit, the number 7, and we've digitized it to a 16 by 16 pixel grid. And so we feed in all of those pixels as our input data, and we want to know, can we predict what the digit is? So the output in this case would be something like, we want to know it's a 7. Now often in neural networks, because they're statistical machines, we can't get a definitive answer of what the output is. We get some kind of probabilistic one. And all we want to know here, of course, is that the probability that this is a 7, this pixels represent a handwritten digit that's a 7, is greater than the probability that it's not a 7, i.e. it's not a 1, 2, 3, or any of the other digits up to 9, and 0. So we would expect some sort of probabilistic output for each of the potential digits that it could be. Again, we don't have a function for this. There is no mathematical function we can look up that maps handwritten digits or any other thing like doctor's handwriting to medicines or whatever. So again, how do we learn this function? Our third example is the one we started with. We have customer data related to website visits, and we feed those features in, and we want some kind of buying prediction function. We want to know for a given user what's the chances they're going to buy a product. Maybe we're going to use this data to, if we think the product, the probability is high, then maybe we keep everything as it is because they're going to buy the product anyway. If the probability is low, maybe we deploy some kind of intervention, like some kind of offer or some kind of like retargeting ad to bring them back and increase their chances of buying the product. So again, we don't know this underlying function. It can't be looked up anywhere. We don't know what it is. We assume there is one. And so therefore, how do we learn this function? Well, we already said that a neural network is a universal function approximator. So if there is a function to be learned, we believe it can learn it. So the question is, how does this actually happen? So how do we find any of these functions then, these universal function approximations? There are a number of assumptions that are key. The first one is we assume that there is indeed an underlying function or pattern that exists in the real world with the data we're given, and we're going to call this the target function, h of x. Secondly, we hypothesize that our neural network can indeed approximate this hidden function via some model function. So we're trying to make f of x approximately equal to h of x. Without knowing what h of x is, it's going to be driven solely by data. And there's a whole bunch of theory as to why a neural network is capable of modeling functions, and we're not going to go into that. We're just going to assume that they can, and we're going to look at how. Thirdly, we assume that the data sample we're given, our measurements, say of the website visits or the smart city data, is indeed sufficiently representative of the underlying pattern in some general way. When we say general way, we mean that the data we're given is sufficient that we can actually create a model, approximate model, that does generalize to out of sample data. So this is the key assumptions that we're going in with when modeling using a neural network. So a neural network then is some black box that has these kind of like functions inside of it, a network of functions, and we're going to get into what those are later on. And we're saying that the key thing about a neural network is we can adjust the function. So in order to find a function, we can configure the neural network using these, I'm showing them as sliders, which is a metaphor here, like mixing desk sliders or sliders on an equalizer on a hi-fi, if you can remember those, or they could be dials or knobs, whatever you want. The idea is just to show metaphorically that we have some settings, some parameters we can tweak to constantly change the function that the neural network is modeling in order to change that function and see then if the data that we're putting on the input does indeed, as we change the function, give us what we're looking for, in this case the percentage chance of buying our product. So the function then of the neural network is not just a function of the inputs, but a function of these parameters, these sliders, and they're the key things that we're going to change because the data is fixed, the sample data, and by adjusting the sliders we will adjust the model function and see, you know, how well does it approximate the hidden function. So this assumption again is reasonable if there is a hidden pattern h of x in the customer data related in this case to the chance of buying a product, which is our hypothesis about the hidden function. Then some configuration of the sliders might configure a model function that will approximate the pattern. This is our assumption. Is this assumption reasonable? There's a whole bunch of theory and proof around this that we're not going to get into, but the bottom line is that in order for the be reasonable that the function is indeed learning and has approximated the hidden function, there has to be a real world pattern, as we said in our earlier assumptions, but there has to be a sufficiently large sample of data that it represents the hidden function and enough sliders that we can configure our function to in some way fit this hidden function that exists in the real world, and then we can use that to make out of sample predictions with some degree of confidence. So there are proofs that say this is possible. You can look them up, things like PAC learning, PAC, probably, approximate, correct, and it's a whole bunch of math theory as to how a configuration of a system based upon a sample of data can indeed tell us something about the out of sample data. So what is learning then? It's using this sample, this data, to discover an optimal function that generalizes to h of x. That's what we want to do. That's what we mean by learning. We assume access to historical measurements, otherwise how are we going to find out what the relationship is? So we have some historical data, and we can imagine that nominally as a table of different data points, and each row in that table is a data point, and each column is some different feature, like the time on the website, the number of clicks, the number of saves, what browser they're using, things like that. We also critically assume we do have some actual buying history data. Otherwise, how are we going to find a pattern? If we want to know in what way does this input data relate to the buying history, we need to know what the buying history was historically. And so that's the actual buying history. Then the idea is that once we configure the neural network, it will generate estimates of the buying history. Because we have the actual buying history, we can then compare our estimates with the actual buying history, and that will tell us, well, how well is this neural network actually doing? How well is it modeling the system? So because we're using the historical data to supervise this process, to supervise, for each estimate, how well does it match what the historical data told us, this is called supervised learning. So how do we find this function? Let's just take a kind of naive one idea, we could have a slot machine and just kind of randomly guess a whole bunch of slider settings to configure our function. So we have a number of sliders, we won't say how many, but there has to be sufficiently many, as we said before, to accurately represent the hidden data. We're just going to guess them, and so now we have a guessed function. And then, of course, we can generate predictions. So we can feed in our sample data, see what the outputs are predicted, and then compare that with the actual data. So either the buying history or the traffic density or the digit that we actually labeled if we're, say, looking for handwritten digit recognition. So this comparison is critical. And we're saying here we've just guessed a function, and so the chances of it being right are obviously going to be low. So we need a method to kind of like iterate and improve our guessing. So we can formally measure our guess by computing the error between the predicted output and the actual historical output, and we're going to call this an error function. And then we can compute the error between the predicted and expected values. So for example, let's say that the output that we predict for the first data point is 0.1, where we have fixed this as a probability so the probability of buying the product here is 0.1 or 10%. But for this particular data point, when we look at what happened historically, there was a high chance of buying the product, 0.9. So in this case, our prediction is wrong. It's a poor prediction. So what can we do? Well, we can adjust our sliders, and we may now have improved our first prediction. It's now 0.85. It's close to 0.9. So we could say, that's a good prediction, perhaps. It's within a certain error tolerance. But now, however, our second prediction may be way off. If we predict 0.6 and it actually is 0.1, then this is a poor prediction. So how are we going then to assess the accuracy or the efficiency of our neural network in predicting? It's better if we consider the average of all of the errors or the mean, because then, if most of them are close, then the average is going to be low. So we don't really mind if there's the occasional error, so long as in aggregate, i.e. in average, it is accurate overall to within some degree of error, some tolerance. So we can keep adjusting our sliders and keep guessing at the different functions and keep checking our mean error. And, we're going to get different results. And then when we find a very low error, or the lowest one for all of the guesses we've made, we can just say, well, that's the nearest best approximation we have of the hidden function. Clearly, this is an inefficient method if we're just going to keep merely guessing. So we need some programmatic method that's going to get us there in a kind of more systematic fashion. So how do we then adjust these sliders to minimize the total error? Is there a mathematical approach we can use that's better than guessing? Now we note here that the error function is a function of the inputs and the sliders, the parameters, and the target variable y. And in our case, the inputs are fixed. We already have all of those fixed, so they're not changeable. The only thing we can change is the slider settings, our parameters, to alter the function and see, okay, for each set of sliders, how does the error function move? Does it move up or down? And so we're really trying to minimize this equation, the error function, with respect to the slider values, the parameters. So say we had a system with just one slider. It's not going to be a very useful neural network, but let's go with it. It has one slider, and we can move that around, and then we can move it up and down its whole range, and then we can plot out what the error function is. And we can see here the error function is shown in purple. And for any particular slider setting, we can read off what the error is, as is this grey point shown here on the graph. And we can move the slider around until we find the position where we've now got the lowest error. So this giving us some sort of mathematical clue here that if we do know this function, if we can somehow gauge where we are in this function space, we can try and find where is the minimum mathematically. And maybe if you remember your calculus, you're already getting a few ideas or hints as to how we might do this. Let's imagine though that we have two sliders. We can do the same thing. We can move the first slider and look at the error function with respect to just the slider 1, find where it's its lowest. We can do for the same for the slider 2, and thereby for the function as a function of these two sliders, we can find the overall minimum still, and we can keep going on. We could add in a third slider, a fourth slider. Of course, we wouldn't be able to visualize it like this once we get beyond two sliders. But that doesn't matter. The principle is the same. So then now we have a strategy. We find the minimum of our error function with respect to the sliders. But how do we do this? So the big question here is, how do we find the minimum of a function? Ignoring for a minute that we don't know what the function is, we'll get to that. So if we remember our calculus from high school, if we have a function here like a parabola, f of x is equal to x squared, how do we find the minimum of that? We can probably remember this from calculus. We can compute the gradient, which here we're showing at some point where x equals 2. The slope of the function at this point, we can just plot the tangent to the line and then look at the height over the width, or the rise over the run, which is a over b in this case, and that gives us the slope at that point. And then we can then look at where on that function is the slope equal to 0. And there's a more precise way of doing that, which is differential calculus. So if you remember from high school math, the differential of x squared is 2x. That's the actual function now of the slope. And we said if the slope's at 0, that's the minimum. So we set that to 0 and we ask, what x gives us 2x equals 0, and the answer is x equals 0. So if our error function was a nice equation like the error of x is equal to x squared, like this, we can just do differential calculus and be done with it. So now we have a method to find the minimum. We use differential calculus. However, the problem is, the challenge number 1 is we don't have a convenient function. As we said at the beginning, we don't know what the hidden function is. We're approximating it. And that approximation is some very complex network of functions inside of our neural network, which we'll get into later. It's not something that's analytically solvable because there is no convenient function like x squared. So therefore we can't use symbolic or closed form or analytical math to compute the slope and find the global minimum. Even if we could, it's an intractable problem. So here we can see maybe our error function is this kind of messy thing we're showing here. What's the equation for that function? We don't know. So we can't write the equation out for that function and then just do the differential calculus and set it to 0. We can't write the function out. The second challenge is we could have so many of these sliders. In the case of a large language model, billions of them. How are we going to manage that? That's intractable. I mean, we would never be able to write an equation out and do the differential calculus for that. It's just absurd. So it's completely intractable. So we have to ask, is there a software method, a computational method that can compute the minimum for us? And now we're getting towards the magic source of learning. So we could use brute force. Let's say that's our sort of starting idea. What do we mean by that? Well, we can wiggle, and we're showing here for just two parameters, two sliders. We can wiggle each of the sliders independently and see, okay, if we wiggle it, slightly to the above or slightly down, if it's an up-down slider, did the error go up or down? Now, if we moved it up and the error went slightly down, then we say, okay, that's the direction of the slope approaching towards the minimum. And we can do that for both the sliders or all of them. So we can say in which direction did the error go down, slightly up, slightly down on the parameter, and then we can adjust the sliders in that direction independently, all of the sliders, and then we ought to be moving slightly down the slope towards the minimum of that function, even though we don't know what the function is. And this method of wiggling each of the slider a tiny amount and then seeing, which direction did it go down, is called finite differences. So we could keep going one wiggle at a time. Wiggle, update the sliders, wiggle again, update the sliders, wiggle again, update, keep going, wiggle, wiggle, slide, up, down, wiggle, wiggle, until we hit a minimum. In other words, wiggling the sliders is no longer causing our error to go down, and maybe it starts increasing again, which means we've gone up the other side of the valley or the slope. So where we hit the bottom, we found the minimum of our error function, and this method, as you can see pictorially, is we wiggle, 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 find where the setting is, and now we have the optimum setting for our sliders where we found the minimum. And this technique is called gradient descent. We're descending the gradient one bit at a time, iteratively. What about local minima? You might ask, well, don't we get stuck? Because, if we're wiggling, we could get to a point where if we wiggle a little bit more, the error goes up again. And that's because we caught in one of these little dips. So as you pass from one side of the dip to the other, the error goes up. So you might stop the process at that point and think, oh, we've reached the bottom, whereas actually we only reached one of these local minima. Now, it turns out, and there's lots of analysis of this, it's even an ongoing subject of research, that in a high dimensional space, if we have lots of these sliders, at some point where we do find the minimum error, it turns out that is sufficiently good that the neural network has indeed approximated the hidden function. We may be stuck in a quote-unquote local minima, but in all intents and purposes, it's as if we have actually found the global minima. And there's plenty of theory you can read about this subject. So this wiggle method then, this wiggle method has issues, this finite difference. Number one is it's inaccurate. This finite differences are just approximations. And those approximations can accrue to drift off in terms of accuracy. So we could end up with inaccurate gradients. Obviously, if we knew the actual slope analytically, like x squared, we could do analytical calculus. So the differential of x squared is 2x. That gives us a precise value. So maybe there's a way that we can still decompose the problem into lots of smaller problems where the math is knowable and we can use precise algebraic evaluations, and that would overcome this accuracy problem. The wiggle method is also highly inefficient, almost actually intractable at scale. The number of wiggles you have to do, and it would take forever to get there. Moreover, the way that these wiggles accumulate as we add up all of these wiggles is, mathematically speaking or computationally speaking, the numbers inside of the computer, inside the CPU, they become unstable, which means they become ridiculously small, and therefore we no longer actually can model the problem within the precision that we can cope with inside of our CPU. So now then, for the cool way, backpropagation. And to understand backpropagation, that's the subject of part 2. So please join me for part 2 of this short talk where we go into the kind of magic of backpropagation. Thank you for listening.